physics time. We're still talking about Newton's laws. Let's call this one Newton's laws 2 plus friction and gravity. We'll talk a little bit about gravity, but the main thing we talk about gravity will be in a later chapter. So first of all, why don't you, as I said, tell me what Newton's laws are. I think the objective is illustrate the relationships between Newton's laws of motions. Let's write that down too. Illustrate the relationship between, probably that should be among, right? Because there are more than two of them, right? Among Newton's laws of motion. Now, tell me Newton's laws of motion. Why don't you summarize them? The first one in one word. What is Newton's first law of motion? Inertia. Inertia. Yeah, say the whole thing, Tatum, like you were about to. An object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an unbalanced force specifically. Number two, how do we express number two?
Acceleration.
Yeah, force equals mass times acceleration. The way we can express that is that the direction of a net has to be net force too. The direction of the net force on an object is also the direction of that object's acceleration, and it's inversely proportional to the object's mass. For a given force, the harder you push on an object, the more it accelerates, but it's inversely proportional to mass, meaning that the larger it is, the harder it is for it to get accelerated because of inertia also. And then number three, yeah, this is force interactions. For every action, there's an equal and opposite reaction, and together we call those an interaction. So what we sometimes call the action and the reaction together are actually an interaction. There's no such thing as a single force in the entire universe. There's always an interaction. Let me give you some examples. If I push on the board, the interaction is, that's half of it. I push on the board is half of it. What's the reaction? The board pushes back on me. But actually these two things are one. It's one force acting in two different. You see what I mean? It's the same thing. Here's where it gets a little tricky. What if the action is the earth pulls the mark? That was really loud. The earth pulls the eraser to the ground. What's the reaction?
The eraser pulls the ground to it.
Yeah, the eraser pulls the ground to it. The eraser pulls the earth up toward it. And that almost to us seems nonsensical, unless you think about it this way, and think about it in terms also, put F equals ma into your brain box here too, that if you have the marker, this is not a marker. This is an eraser. You have the eraser falling to planet Earth. This is obviously not to scale. Did you guys know this isn't to scale? Here's the eraser falling to planet Earth. Compared to planet Earth, what is the mass of the eraser?
Very tiny.
Yeah, little baby mass. And the Earth has a big mass. So we know the force must be the same. That's what Newton's third law is telling us. And this is F equals ma. So we know the force must be the same. F equals F. They are part of the same interaction, right? So F, in the case of the marker, I'm sorry, I should have made sure to draw that F the same size. In terms of a marker, what's the marker's mass? Tiny little mass. Same F, same force. But now the Earth's mass is great big. So how does the marker accelerate? Yeah, it goes down, but it has a great big acceleration. And the Earth has tiny little, almost no acceleration. That's why this can still be true, but we don't notice the Earth rising up to meet the marker. It doesn't move. It accelerates immeasurably small. It does still happen. And a way we can do that is if we scale up the marker now, the marker is the size of the moon. Does the marker's gravity affect the Earth? Yeah, it's not a difference in kind. It's a difference in magnitude. That is, it's not that the marker doesn't pull on it because it's too small. It's that it pulls on it very, very, very smallly, immeasurably small. If we make the marker bigger, the force gets bigger, and therefore there's more acceleration of the Earth too. Your book says it as, I like the way that your book describes this phenomenon. I can find the right page. It says, here, let me ask you this question. We know the Earth pulls on the moon. Does the moon also pull on the Earth? Yes? If so, which pull is stronger? Be careful. They're equal. They are the same force. Why then does the moon orbit the Earth? That's not actually true. If you, I was going to say if you look at it, but that doesn't really work for this. But the truth is, that they both orbit. They don't, it's not, here's the Earth, and here's the moon, and the moon goes around it in a circle. That's what we have been led to think. We've been lied to our whole lives. What actually happens is that the moon and the Earth both wobble around this little point somewhere between them. So the moon goes around that point, and the Earth goes around that point too. And so the system was like this. Yeah, the system was like this. The Earth does move too. They orbit each other. And you notice that when if they were to be the same size, like in a binary star pair where they're approximately the same size, they just orbit each other. This thing here is called the barycenter. I used to call it the Rick Barry Center, but now he's not alive anymore. So, in an interaction, the forces are always equal. Yep. So I push. Excellent question. I push on the board, and the board pushes me back with the same force. What if I push on? What if I push on this stand? It pushes back on me, but only to a certain degree, right? Can I ever put the same force on this stand that I can if I just lean on the wall like this? No, because the stand will move. The stand will accelerate away. The air won't hold it up, right? If I do it on the air, I will accelerate downward. But even in that little case, even the tiny amount of force that I'm putting on the air is putting that back on me. It's just that the air resistance with my hand is negligible. Whereas, if you use the Kleenex again, if I have this Kleenex here, the force of the Kleenex on the air and the force of the air on the Kleenex are measurable. There's a noticeable balance there. Another example your book uses is this of the rifle and the bullet. That's going to be our little example area over here for today. Here's a rifle. Good. Oh, nice. It looks more like a peace pipe. But we're going to say this is a rifle, and it has a certain mass, M, and there's a bullet in it. And the bullet has a certain smaller mass, baby M, right? When the cartridge is fired, and this explosion happens here, the same force is applied to both the rifle and the bullet. Why does the bullet move more? Smaller mass. So is a good solution to the problem of, oh, my bullet, I don't know, what do you people use guns for? Death. My bullet didn't kill the thing. Is a good solution just to get, I'm going to draw a rifle again. This time it's going to be good. Just to get a bigger bullet, same mass as the rifle, what will happen? This won't go very far, and this will be much more recoil. What we would call a recoil is now the exact same acceleration as your bullet is, and so you're going to get exactly as injured in the shoulder as the thing you wanted to cause death to, because it's the same force, and if you have the same mass, now it's the same acceleration too. So generally, we want bullets to be smaller than the firearm from which they're being fired. It doesn't even really make sense if we talk about it otherwise. One of the examples is that if someone, I forget the person's name, in one of your problems, someone thinks they can make a cannon better by making it lighter, and they decide that the best solution is to have it be the same mass as the cannonball. If that were the case, if this is mass and this is mass, and here's you firing the cannon, you're in just as much danger as the person at whom you were trying to person or thing at whom you were trying to fire the cannon, because the cannon's going to accelerate into you, and you're significantly closer. So probably you're actually in more danger because of this relationship between mass, force, and acceleration due to Newton's third law. Another example of this is that now, if we think about it, the example the book uses is turn the gun on its side. Now it looks like a cane, and you fire the bullet. Which way is the gun going to accelerate on firing? Up. The gun will accelerate up. And now, instead of gun and instead of bullet, let's imagine we have machine gun, which I've drawn almost exactly the same way, a machine gun with more bullets. Still going to accelerate up, but repeatedly, right? I mean, every time we fire one, it's going to go up and up and up. Now, same thing, except instead of the bullets are gas molecules, and the gun is a rocket. That's how rockets work. The firing out of the gas the rocket produces causes the rocket to accelerate. This is not at all like a plane or a sailboat or a car or a bicycle that relies on some outside force. A rocket accelerates by ejecting mass. That's why a rocket still works in space and a plane doesn't. The plane relies on Bernoulli's principle to cause it to keep flying. It needs an external force. The car depends on friction with the road to keep going. The rocket is firing mass from itself. Eventually it'll run out and then it won't be able to do that anymore. But while it has fuel, the rocket fires mass out, which causes it to move forward. Okay, here's a little picture of this guy on page 82. He says, wrong way. Honestly, the wall hit my hand and I sprained my wrist. Is that true? I mean, yeah, so logically, or yeah, societally, we would say, yeah, but physically, dirtbag, yeah. Physically, we would say yes, that is true. That is actually what happens. That's it's not the hitting of the wall that hurts the hand. It's the wall hitting the hand that hurts the hand. But once again, they are both part of one interaction, and so that's a kind of meaningless distinction. It's dualism when we really should be approaching monism. It's his fault. He was the one with the agency. Now let's talk a little bit, as I said we would, about friction and gravity. Both we talked a little bit about gravity already, but let's talk a little bit more about friction and gravity and how these things relate to this. Remember, they're always part of a force interaction, but specifically about friction. Friction is let's say we have, here's my music stand. Nice. That's actually a pretty good drawing. Here's me. Yep, that's me. And as I push on the music stand, Newton's first law tells us that almost said Newton's third law. Newton's first law tells us that an object in motion stays in motion and an object at rest stays in rest unless or until acted upon by an outside force. And so if I push it, why does it not stay in motion? Because of friction. Because of friction. So if I had this on a frictionless surface, it would you can see even when I naturally lift it out of my way to where I lift it up a little bit, because two things go into the calculation of friction. F sub F, friction, equals the normal force times the coefficient of friction mu. So F sub F is the force of friction. F sub n is the normal force. And mu is the coefficient of friction. What is the normal force measured in? What unit measures the normal? No? Newtons. What is the friction force measured in? Newtons. And so coefficient of friction must be? No. Because otherwise force of friction would be Newton squared. No. Coefficient of friction must be unitless. It's just a coefficient. The coefficient of friction is provided on any problem where you're doing this. You'll be given a coefficient of friction. But there are tables. I mean, there are tables and tables and tables online of the coefficient of friction of any two given surfaces. So the steel on wood of this action, of my music stand, would have a certain coefficient of friction. I don't know what it is. Let's say it's 0.3. F sub F equals F sub n times mu. Let's say that the normal force, well actually let's just do the coefficient of friction. 0.3 is the coefficient of friction. It's unitless. The normal force, in this case, because I'm on a, or I already drew this, so I don't need to draw it again. Because I'm on a horizontal flat surface, which direction is gravity acting on this? Always down. Always down. Is the normal force always up? No. The normal force isn't always up. The normal force is perpendicular to the surface. But since my surface is horizontal, in this case, which direction is the normal force? Up. And it's mathematically equal to the weight. So let's say the weight of this stand right now, I don't know, let's say that's, let's say it's 400 newtons. Let's say it's 400 newtons. The normal force, which in this case, not always, but in this case, in the case of any object on a horizontal surface, is the same as its weight, is 400 newtons. So what's the force of friction acting between these two things? Well, it's 400 times 0.03, which is 120 newtons, would be the force of friction. Sorry, 0.3. 0.3. So how can I overcome friction? Well, I could just supply the friction force of 120 newtons required to do that. What else? What could I do to reduce the friction between these two things? I could make it slippy. What do you call that? Greasing it up. The professional and scientific word is lubricate. I could lubricate it to make it so it doesn't have as much friction. I could use grease or even water to some degree as a lubricant. Oil, yeah. I could, but some kind of lubricant, what it does is if we look at this microscopically, nothing is perfectly flat microscopically. And so if we look at this microscopically, when they're just sitting there, these two lumpy surfaces kind of get into each other's cracks, and it takes a little bit of force to get it past the cracks. But if you lubricate it, it separates them out, and now they're sliding past each other on a more or less puffy, I don't know, like there's a layer of cushion between them almost, provided by the lubricant. The lubricant. That's one way. So we can reduce the coefficient of friction by lubricating. What else can I do? If I really wanted to move this, is it advantageous for me to do that? No. I can lift it up a little bit, which reduces the normal force, right? I mean, in that case, I just lift it all the way. But if I lift it up a little, I reduce the normal force. And if I press down on it, yeah, I'm increasing the normal force, and so it causes the friction force to increase also. Do you see the relationship between these things? One example in your book is, which of these is the better guardrail? Maybe you've already seen this, but which of these is the better guardrail? There's a car there, the outline of a car, and there's a concrete guardrail, and there's a wood guardrail with a metal thing on top. The concrete guardrail is better because it's concrete, and it's going to touch what part of the car? The rubber, yeah, concrete on rubber has a higher friction coefficient than the metal, which is going to, the metal on the metal of the car will have a lower friction coefficient, and probably the amount of normal force will be greater on the car one too because it's covering a larger surface of the tire. Either way, at least your tires will be what's damaged in the concrete example. Your book also goes on to talk a little bit about air resistance, which is a type of friction, but I'll trust you to read that on your own. There is a pretty neat equation for air resistance that is not given in your book, but it has to do with the cross-sectional area of the object. Like you remember my example about these two things, if I drop them both. The reason that the Kleenex falls slower is not because the marker is heavier, it's because the Kleenex has more air resistance. Has to do with several things. The density of the fluid, the air, the cross-sectional area presented, that's probably the main one in this case, because then if I crumble up the Kleenex, I'm reducing its cross-sectional area, it'll fall faster. But the cross-sectional area presented, the speed of the object, which actually gets faster, obviously, as it falls. And so at some point, there's terminal velocity, which is when the force of gravity and the force of air resistance are balanced on an object, and it's going at a certain specific speed and no longer accelerating. But the other thing we want to talk about real quick is pressure. Pressure equals force over area. Pressure, P is pressure, F is force, and A, capital A, is area. Area we measure in square meters. Force is measured in newtons. 1 newton over 1 square meter Remember, a newton is about 1/5 of a pound, and this is a square meter. So here's 1 meter. Look at here real quick. Here's 1 meter. If I turn it this way, you can imagine the square encompassed by this meter on both sides, right? You can imagine a square that's this size on both sides. Yeah? So like the imaginary square I'm encompassing by having this be its width and this be its length. The force of 1/5 of a pound on that, maybe the weight of this marker, over that large of an area is a very, very small number. That's called a Pascal. We usually use kilopascals when we're measuring pressures in real life because Pascal is such a small number. What's going to hurt more, Justice? What's going to hurt more? To poke yourself with the same amount of force with the eraser of a pencil or the pointy end of a pencil? Why? You're using more force? No. The force stays the same. What's changing? The area. The pencil, the tip, the pointy end, has a smaller area, and therefore the pressure is greater. Would you rather be, if your mom is gonna stand on your head, would you rather her wear her high heels or her cowboy boots? Cowboy boots, because the high heels are gonna have a smaller area and therefore more pressure, and then your brain, you get a lobotomy. So you get a lobotomy. I think that fairly well covers everything. There's obviously quite a bit more specific cases of these things in here that you'll need to read about on your own. But do you have questions about any of this? I mean specifically about Newton's 3 laws. We talked about inertia mostly in the last chapter. But do you have questions about friction or Newton's second and third laws? Remember, and we talked about this in a couple of videos back, but remember that forces are also vector quantities. So you will do vector addition on this. Let me give you an example. Let's say Justice is the running back for the football team.
Never gonna happen, but yeah.
Justice is, look how happy he is too. And he gets tackled with a force of
10 trillion.
500 newtons, let's say at an angle of 230 degrees by Carter.
All right, now make me proud.
And at a force of 750 newtons at, what is that going to look like? More like 23 degrees from another big fella.
Mitchell.
Mitchell's not big, and he's
Mitchell's
broken.
not big, but he's one of the biggest.
I guess Roman. Can we add these forces together? Do you remember how to do that? Sorry, 220. Oh, I did do 23 degrees. Sorry. At 23 degrees. Can we add these forces together? Do you remember how? We break them into components using trigonometry. X and Y. Yeah, we add the X and Y's together, build a new triangle, and then we get a resultant.
And then I'm